Okay, we're now at the sixth video of this series. What have we learned so far? Sadi Carnot was interested in developing the idea of the theoretical maximum efficiency of a heat engine. Now, of course, at the time he was working, there were only two kinds of heat engines. One was involved gunpowder, and that would be a rifle or a cannon or some other weapon. And the way that worked, of course, is that you ignited a charge of gunpowder in the barrel of the gun. The gunpowder would burn. You'd have hot gases expanding. The hot gases would expand against the bullet or the cannonball or whatever and propel it out the barrel. And of course, the other heat engine was the steam engine. Steamboats, steamships, steam locomotives. So how do we figure out the theoretical maximum efficiency of a heat engine, of a steam engine, and why are we even interested in that subject? Think about this. Why would anyone really want to know what the theoretical maximum efficiency of a steam engine actually is? It would seem that we had steamboats that could go on water, steam engines that could power factories, steam locomotives that could haul trains. Why do we need to know what the theoretical maximum efficiency of a heat engine could be? Well, that's an interesting story, and I'm going to talk about it later. But right now, let's think about what other kinds of engines would have been familiar to a person in the 1820s. And what comes to mind, or what I hope would come to mind, is a water wheel. Now, a water wheel can be thought of as taking a substance, in this case water, from a high energy reservoir, spilling it or allowing it to fall around a wheel, or pushing a wheel, turning a wheel, doing work, and then discharging into a low energy reservoir. Think about this: high energy reservoir, work, low energy reservoir. We go from a high energy reservoir past a device that extracts the work, and we spill the water out into a low energy reservoir. Sadi Carnot's father was a military engineer in the armies of Napoleon, but during his civilian career he was also an expert on water power. And one type of water engine that was being developed at the time involved a piston and a cylinder. So we take water from a upper reservoir, high energy, high gravitational potential energy, spill it into a piston, or cylinder piston arrangement, make the water as it's falling do work on this piston, make the water as it's falling do work on this piston, and then discharge the water into a low energy reservoir. This is, of course, a key idea in the development of the Carnot cycle. Now, before we get into the actual Carnot cycle, let's think for a moment about water power. Water wheels give us an immediate way to measure their efficiency. Let's imagine that we have our high energy reservoir. We're spilling out, making a water wheel do work, and discharging the water into a low energy reservoir. If we connect this water wheel to another water wheel, and we use this water wheel to pump water back up to the high energy reservoir, you should know from the laws of thermodynamics that we're never going to get 100% of the water pumped back up. What percentage of the water could be pumped back up to the upper reservoir from the lower reservoir is a measure of the efficiency of our water engine, of our water wheel, of our water piston and cylinder arrangement. So it gave people a way, right away or immediately, of thinking about how efficient an engine could be in which water falls from a higher energy reservoir to a low energy reservoir. In our next video, we'll actually get into the Carnot cycle and talk about what happens in our theoretical maximum efficiency heat engine.